So I'm yours. I don't want to do more integrals.
Is there any way around the residue, meaning that's what we're going to use every time we have this kind of singularity or multiple singularities?
Well, you know, if I really taught a complex analysis course, the tractable things are there's three kinds of singularities. Poles. What's good about poles? You can understand if you have a function that has a pole, then inverse of the function has a zero. And as you approach that zero, you can approach it from any direction and you get the same pole. So it agrees with our basic principle that derivatives, infinitesimal approaches should not care about direction. So that's why pole is singled out. Pole is isotropic. Doesn't matter how you approach it, you only need the radius of the region to evaluate the pole, the circle integral. Now, the moment you have something that looks like z minus z0 to the power, which is not an integer power, then you have what's called a branch cut. And the simplest branch cut is when that root is 1/2, because very often you end up taking square root of something and studying. So if I, did more honest complex analysis course, I will also go through the same calculation for a branch cut. And first I would do 1/2. It's done very nicely in the book, so I don't feel guilty not doing it. And that's a very typical calculation you have to do. So poles branch cut, and then the third kind of singularity is essential. It's crazy, it's wild, it makes no sense. Everything fails when you have essential singularities. So what people do in complex plane, they make sure that the contours avoid them. So they get nice results as long as this land where dragons live is avoided. So that's, these are the basic prescription of how to convert any integral in integral complex plane. Now in real life, no matter what you do, you won't be able to do integral analytically. Because in real life, it doesn't, all the integrals we teach in our courses have been done in before 1850. But all the integrals that you will compute when you have to compute material properties of gold on graphene, something, in Uzi Landmann's floor or in any condensed matter theory group, you will have to put it on a computer. And there are programs for that got Nobel Prizes. So doing those integrals, Walter Kahn and somebody got a Nobel Prize for explaining how you do this.
A physics Nobel Prize?
Yeah, sure. Or maybe chemistry, but I think they're physics, I forget. And, well deserved. I mean, it requires, what physicists are often good at or should be good at is to know what approximation to make, what to throw away. So, it's not just that they wrote programs, but they thought very carefully what you can throw away so you can put it on computers. And I will next week continue a little bit with another very important application of contour integrations, which is called asymptotic series, which is precisely, what happens when you have essential singularity? How do you deal with that? And so, we'll spend a week doing this kind of thing before we leave the complex land. And go to beautiful application of complex numbers, which is Fourier analysis.
So I don't know if you could do this right now, but I think it would really help me if I saw like the big picture, right, of what we've gone through so far. So like maybe a tree diagram or like a flow chart of like, okay, you're working in the
Yeah,
complex plane, you have a function, let's say it's
I'll go.
perfect, and
I'll
then
go a little bit further back.
okay,
So my complex, I wrote a kind of a poetry which is on the homepage, zero. What's the grand scheme? So this particular course in mathematical method has a grand theme that in your work you'll have to deal with matrices, often very large matrices. No matter what research you do, it doesn't matter whether it's quantum mechanics or you're doing image analysis, you will find yourself trying to understand large arrays of numbers of data in context of linear problems. So that's why I taught you matrices, eigenvectors, eigenvalues, and singular value decomposition. That first branch was that in one case, if you have situations where you repeat doing same thing, you do that often in physics where you apply same law of motion to step forth in time. Then you use eigenvectors, eigenvalues, because a huge problem becomes one-dimensional when you do that. Now, if you're just given a pile of data and you have to find out what are the large numbers, significant numbers of that pile of data, then singular value decomposition will pull out from your data important directions. They're called singular vectors, and approximate data by some ellipsoid where you'll be able to do dimensional reduction, meaning you'll be able to throw lots of directions away because they're so small, they're not important. So that was the first, branch. We will have to deal with large arrays of numbers one way or the other. And there are two versions. One is that happens in solving various electromagnetic, quantum field, and similar problems where you have to involve something. That's eigenvalues. Eigenvalues. The other one is find what's important feature in the data. That's singular value decomposition. If you read literature, singular value decomposition is extremely important because we are doing lots of big data analysis, and Google engineers use them. Then I said, well, to understand matrices, one-dimensional matrix is just real numbers. We know that. So the next one is two-dimensional. So it's one exercise, I showed you that there is a special two-dimensional matrix which explains how you rotate in a plane. It generates rotations. But it turns out that matrix has an interpretation of a complex number. It turns out that Gauss visualized action of that matrix as acting on two-dimensional vectors, which are complex numbers. And that particular matrix was the rotation by I. And so we went into the direction. Suppose, we look at, the world generated by this little matrix called imaginary unit, which was very imaginary until Gauss realized you can think of it as a two-dimensional matrix. And it turns out, amazing things happen with this matrix, because if you assume that you do that and you also define problem to be something that doesn't care about how you approach points in a complex plane, that was called Cauchy-Riemann, then came all the structure of complex analysis. And there are two parts of it. First one is always what we do is always look at small infinitesimal structures. Since Newton and Leibniz, we have learned that this is a smart way to proceed. Look at what small changes do. That gives us just Cauchy-Riemann relation, saying that we can pretend that derivation with respect to two-dimensional quantities same as derivatives with respect to x, as long as Cauchy-Riemann is satisfied. So it allows me to take any function of x and write it as any function of z and all derivatives, all the, I taught you that a function of a matrix can be defined and all the functions of this two-dimensional matrix can be defined. So everything just goes into two-dimensional space, which is complex plane magically. Number one. Number two, we have to, piece the infinitesimal parts together. That's called integration. And it turns out because of this orientation independence, you can integrate any way you want in a complex plane because they're all equivalent, because they don't care about orientation. So this is, the magic of contour integrals. The first version is a contour integral without a pole in it, or a branch cut, or essential singularity is always zero. So that's a very amazing way of writing zero, because on the left-hand side you can put arbitrarily complicated thing. So then this week is, giving examples how to cookbook recipes, how to take integrals you need to do, complexify them, and make them add up to zero, and then express them in terms of pieces that you can easily compute. While the original integrals are horrifying because they are integrals over oscillating sequences. So the integrand doesn't go to a limit. It oscillates. Still, you can integrate once you go to complex plane, because oscillations along the real axis become exponentials, decaying exponentials along imaginary axis, because, on the real axis, sine and cosines are sums of e to the I theta. But if you turn the contour, that becomes e to the minus on imaginary axis. So you can replace all the oscillating integrals by decaying exponentials. Those guys are nice, smooth, and that's the essence of all the tricks with it.
Okay.
And
so
I'll do one more trick, which is not obvious, which is called asymptotic expansions, that I do next week.
if I could add one thing just to see if I understand correctly. So if you have a tricky integral in the real axis, right? So that's just a 1D sort of problem, right? But then it's like, let's use the power of the complex plane. So now it's a two-dimensional problem. Let's just make this a contour, make this line a contour, closing it.
The trick is that you know how to write the function of the matrix. In this case, complex numbers are 2x2 matrices, actions. So we learned that in the beginning. Whenever I give you a function of ordinary number, you say, well, I can put a Google matrix inside of it and it still makes sense. So that's step number one. Step number two, once you have this, you can turn it into contour integrations. And those are amazing because they don't care. You can turn something on a real line, you can just move it off to complex plane and find it's extremely simple. When
So it's very difficult to just calculate the original integral is you can think of it as the section of the contour on the real axis, and that's really difficult to calculate. So what you do
itself, it's impossible or horrible, or you have to be very clever to do it, because you have to average over oscillating things with changing weight as you go. But this now moves it off to the complex world where the truth is obvious. You keep getting all these pi's. Now, why the hell should you be getting pi's integrating from minus infinity to plus infinity? Because they're related to circular contours, once you go to the complex world. But on a real line, it's just mysterious. Why pi? I integrate 1 over x squared plus a squared. Cosine, even without cosine, why do I get pi? So lots of things are very intuitive in complex plane. Now, this is good news. The bad news is that mathematics and physics had to move on from complex tricks at some point because most of our problems are not two-dimensional. They're not in complex plane. And one way we move to higher dimensions will be the Fourier analysis. We'll show that, even when we have a high dimension, we can complexify every direction separately, rather in terms of trigonometric functions or exponentials. And, in this way, we can go on using complex method, even though we are in three-dimensional space or we have Avogadro number of atoms and stuff like that. So that'll be one direction. The other direction will be, we learn some amazing geometry from these complex numbers. Can we use this geometrical idea? So we learned that there is invariant quantity, which was, this damped amphitwist. The cats were mapping into cats of different size and orientation, but they were always cats. So can we use that idea? That leads to group theory in any dimension. So that will get us to higher dimensions and geometries of spaces. So that we'll do for a while. And once we are done, we'll go back to applications in, let's say, neuroscience and God knows what. So the big problem today, just a second, please ask me in a second, but let me finish it. The big problem today is that we are able to deal with huge amounts of data. But when you look at it, it's obvious that only a small part of the data is relevant to what we're interested in. And most of it just garbage. So how this happens, that's called dimensional reduction. How do we take a picture of Alaric, which has, 4 megapixels on it, and how do we express it in terms of, 1,000 numbers or something? And that's, very important, and that's dimensional reduction. So I'll come back to that to finish the course. Jean-Louis has left the call, offended. Okay, never mind. You're here, yeah. So one picture is worth 1,000 words. I agree. That's why I'm drawing this picture.
Especially if it's a curve being rotated by an amplitude or something like that.
Alaric and I understand lots of things. Unless we have a picture of it, we find it very hard to understand. So this picture is something about how we convert any problem into a finite dimensional matrix problem. So what we do in practice is if we have some smooth function of space in any number of space directions and time in this particular case, only way we can deal with it when we stick it on computer is to evaluate the value of the function on a lattice of points in space-time and represent the smooth function by, its discrete values. We have no other ways to do this. So that's the picture which makes me understand what a discretized version of a problem in quantum mechanics is. Now, the important part of this picture is that the function is smooth, it's differentiable. It might be even holomorphic or meromorphic, who cares? And it could be, a set of functions. It doesn't have to be one. But the simplest one is so-called scalar function. So how do we exploit that? We write the function as a sum of oscillations in which the most important, the smooth oscillation, because this oscillates, only 1 or 2 times across the thing, and then there are finer ones, and that's called Fourier analysis. So in that case, dimensional reduction says if I have smoothness, I write it in the space, I get a bunch of discrete points, but if I Fourier transfer them, I'll find that only few Fourier modes are important, and so on. So, the matrices come in all the time, and I'll teach you Fourier analysis on discrete lattices first because it's easier to understand, and then bring it to usual. So that's a picture worth 1,000 words. Alaric, did you have this in mind or something else? If you can draw a picture, you can communicate it. If you only write formulas, it's very hard to communicate. I mean, we can all do manipulations, but the intuition is so hard to get. Again, for
A
me,
single
intuition is...
a single picture with the main telescope on top of Howie, I think it's
Yeah.
50 megabytes each.
Yeah, and that's small amount.
And so it costs a lot to see very little, from my experience.
You mean the universe, you consider it very little?
The picture of the black hole. I remember
Oh, it can't even do that.
and the guy is
Yeah, the
talking,
black hole is
and I'm like, okay, this is not a focus. Like, what's going on? Is this gonna get better? And he just left the picture. Like,
It's like 1
where's the
pixel.
picture?
Well, we have a good Earth and Atmospheric Sciences department. They have amazing data because every second terabytes of data are being downloaded because there are all these satellites going around measuring the cloud, the temperature, the chemistry of the planet. So for this planet, we're getting terabytes and terabytes of data per second downloaded and distributed over the world in various, repositories of this information. And from it, we would like to predict weather on the short term and predict climate, the average behavior of the planet on the long term. And it's an amazing dimensional reduction problem. So if you can replace that data by a set of, templates of saying, I'm seeing this or that or that, and just give them names, that's an amazing dimensional reduction. And that's what we're all trying to do. We are replacing the data by mixture of numerical simulation of Navier-Stokes and other equations, plus corrections due to modifications in the measured data. That's called data assimilation. And all of these problems are trying to go from terabytes, to the pictures you can see on your television screen about hurricanes, etc. So these are, this is what we do today. I mean, if science is any good, the data has gotten extremely cheap. Storage has gotten extremely cheap. The thinking is very expensive. That is a bottleneck. The computers will not do your thinking. You have to figure out. So this course is trying to be modern in that sense, and not just 19th century. There are bits of it that we use from 19th century, but the bits, are so modern that they're 5-10 years old.
My suite mate, who actually is a computer science guy, he's working on AI. Maybe I should bring him in to talk about how smart he thinks computers will get soon.
Yeah, sure.
He thinks in maybe 5 or 10 years, computers will be able to write basic programs of their own, and all the people writing those the sort of low-level software engineers will be out.
Possible, but it won't be a great loss. Also, people who used to dig potatoes are out, and nobody misses that particular work. So, there's lots of menial work in maintaining, and incredible amount of horribly written code to maintain our civilization. And yes, if he is right, it would be great. The problem with artificial intelligence is that, it's littered with corpses, because since the 50s we are making outrageous claims, and many of them haven't worked out. But in recent years, the For example, if you watch this on YouTube, the captioning is amazing. And they understand even me. I'm an immigrant. I speak horrible English. That happened within 5 years, 10 years. So I have to give my hat off. Some of the stuff they're doing well. It's brutal, stupid, but they're successful. Other ones, will never work as computation. It'll be always interaction, I think, with human mind. We always have the science fiction idea that the matrix will take over and we'll be just little stupid cats in a big computer game. Maybe. Maybe. I don't know.
Okay. At this point, I'm getting us way off topic. I don't know if you guys have time, but I'm just want to say one thing. Actually, I was talking to my suite mate as well about this.
Anyway, bring him next week, at the end of the lecture, and we can discuss with him.
Okay. Yeah. So we were talking about VR, virtual reality technology, and basically the goal, at least the ideal goal for a perfect virtual reality experience, a perfect virtual experience, is that it exactly simulates reality. And so for that to happen, it has to basically input to all of your senses. And in some sense has that control over you. It has control over all of your senses because it has to stimulate the physical feeling in your body and all your senses. And so then the ethical question arises of, if you allow the system to give that much control over you, what happens when the system either malfunctions or becomes intelligent enough to deny you control over yourself, right? To basically lock you into the virtual world, right? And not let you escape or something like that. So I think there's a lot of ethical questions, and I think the ethics of this has got to catch up to the technology at some point. Otherwise, we're in trouble.
Yeah.
Should it simulate pain for some games as a learning mechanism, right?
Yeah, I'll be impressed when the smell starts working, because it's an organ that's vastly underestimated, because, our language doesn't describe smell very well. We don't verbalize it. That's extremely important for reproduction and everything that we do. So when this virtual reality brings in sense of smell, that's credible. I'll be impressed. But I don't know. It's always working this way. We have our science fiction ideas, which are naive, and then the reality is much more horrifying. So, we are being run by Facebook, which happens to be an evil organization. And it wasn't, it came out from some stupid dating game at Harvard. Just like the thing that is running us, and it doesn't have a virtual reality quality, but it's certainly changing our reality. So it's almost always the unintended consequences of these things. So the positive thing is of the virtual reality, if I've lost my limbs and, I have to function in the world, right? Or lost my hearing or seeing or something. A good virtual reality could restore it to me. We are already able to rid off motor control from people who have lost limbs and, enable them to control robotic movements. So that'll be the good stuff. The bad stuff will come along with it as well. And we are just a child's game compared to biology, right? What you can do by screwing up genetics is infinitely worse than anything that computer scientists can do. So the ethics is absolutely essential, and we don't teach it. It's hard to teach. I have a friend in Earth and Atmospheric Sciences that teaches the ethics course for them, but it's hard to, it's really hard to do well, because it's like teaching congressmen ethics, either you're ethical or you're not. It's very hard to see how to teach it. However, complex integrals I can teach you, so that's what we do here. Okay, we have totally gotten lost. I will delete almost everything that happened. Bye. And we continue next week.